Hi, my name is Chris Nova. Second time here at FOSDEM presenting. I gave a talk last year. Show of hands who have seen it. Yep, it was a good one. We explored, well, y'all ran the track, so thank you. But we explored some anti-patterns and some exciting things in Kubernetes. Since then, Kubernetes has grown a lot. I've grown a lot, and the entire cloud-native ecosystem has also grown tremendously. So we're going to be looking at some more concepts tonight, something that I've been thinking about and studying for about the past 6 months. And we're going to look at some cloud-native computing foundation, open source tools, including Kubernetes, including the Open Policy Agent. And I'm going to try to be diligent about calling it the verbose name Open Policy Agent, but you might hear me refer to it as OPA or OPA as well. And some other exciting tools in the ecosystem, including the Linux kernel. So to start off, shout out to my friends over in this section who gave me some delicious cookies and chocolate before I came on stage. And also we have the 2 Falco maintainers here in the front that have some Falco stickers, and Francesc and Matcha have some over there. So throughout the talk, if you see stickers come your way, feel free to grab one and stick it on your laptop. And you're going to be learning more about Falco and these other projects tonight. So the first thing I'm going to do is I am going to open up my slides. Okay, so this is our first slide here. So yeah, it's called Fixing the Kubernetes Clusterfuck, which I think is a funny way of basically alluding to Kubernetes is complex. And it's complex for a good reason. And because of this complexity, it actually is a very powerful tool, which is why I've been working on it, and that's why I love it so much and why I've been so diligent about being involved with it and using it. So in a weird way, this complexity can potentially scare folks or cause problems, but we're going to be looking at concretely some ways how the complexity, particularly around security, is something that a lot of people that I've noticed may not be necessarily an expert on. I don't even know if I would call myself an expert, but I've been studying it for quite some time, and I'm going to share with you today everything that I've found. So yeah, I wrote a book called Cloud Native Infrastructure, which is how I got into this whole Kubernetes thing. And one of the things that I noticed in Kubernetes that hasn't really been solved is this concept of security. And like, what does security mean to me? As an infrastructure engineer, it was basically like, I don't want anything happening in my system that I feel like should not be happening or that I don't know about or have visibility into. And I would like a convenient way to control that layer of security. So recently, I've become a maintainer of an open source project called Falco. And I've been maintainers of other tools in Kubernetes and other projects I've contributed across the ecosystem for the better half of my adult life. And all of this kind of alludes to this idea that I fancy myself a hacker in the sense that I see something I don't understand and I sit there and hack away at it until I finally understand it. So the 2 words I want everyone to think about today. The first word is prevention. And the second word is detection. And we're going to really explore these 2 words and what they mean from a security context. And we're going to actually go through and do a live demo where we take a Kubernetes cluster set up with Kubernetes cops with the default configuration. We're going to exploit the prevention techniques. In other words, we're going to hack into the Kubernetes cluster live on stage. And then we're going to look at how Falco was able to detect this malicious behavior. And we're going to look at how we can use what's coming out of Falco to draft policy using preventative tactics downstream to prevent this from happening again. Hopefully when I get done doing this, you'll walk away from here saying, as an infrastructure engineer, as a software engineer, as a general Kubernetes user, I would fancy a cluster to have both of these for a complementary, holistic approach to securing and understanding my Kubernetes system. Okay. So everybody, this is the time where you take your phone out. Everything that I'm about to do, including these slides, including links that I'm going to reference, including talks that I think you should go see, including links to my GitHub, my Twitter. Everybody's getting their phones out now. I'll get mine out just so that you don't feel lonely. And everything is there. So if you go to github.com/chrisnova/public speaking, I'm going to do some remote command injection here by hitting the space bar. And of course, my internet's not working. Hold on. No, it's okay. we're going to need it. I don't use the FOSDEM Wi-Fi, so give me like 2 seconds. But anyway, if you go to this website, at the very top, I changed, there it goes. I changed the title here to go to the actual, oh, there's my iPhone, the link in the repo that has everything that I have checked out locally. So if you want to go and follow along, all of the notes, all of the markdown, everything exists here, including the samples that we're going to be going through tonight. Okay, so let's go back to my slides here. So the first word, prevention. Words that come to mind when I look at preventing unwanted behavior are locks, right? If you want to keep somebody out, you lock the door. It's very easy, it's low-hanging fruit, and most doors and most access to our systems have a concept of a lock on it. If you look at Linux, fundamentally, right, there's different ways of locking either users or applications out of what we do not want them doing in the kernel. Show of hands here, who's created a user in Linux before? Okay, everybody at FOSDEM just put their hand up. Who here has written SE Linux policy? Setcomp policy? Setcomp UPF policy? One person, 2, 3, okay, 4. Okay, so again, if you go and you do some research here, you'll understand that we're preventing unwanted behavior, or at least we're attempting to, and that's kind of the lesson here. If you did not want a user to access something on the file system, you could create a user, change the permissions. There's this whole fundamental paradigm in place that allows you to prevent people from doing things they shouldn't do. You can also do this with an application, right? So setcomp BPF actually gives you a way to go through and control which system calls an application could or could not execute. If you look at C groups, right, in the Linux kernel, you could define arbitrary limits for what you want applications that are running within the context of the C group to be bound to. And if they violate this limit, the kernel is going to terminate the process. So we have these fundamental paradigms in Linux that we're all familiar with, and if you follow along in Kubernetes, you will see the Kubernetes and cloud-native ecosystem is following in the footsteps of the Linux operating system. Setconf is to Kubernetes, as OPA, Open Policy Agent, is to cloud-native. Or I'm sorry, setconf is to Linux as OPA is to cloud-native. So that's this concept of access control, policy enforcement. We also have this idea of image and artifact scanning, right? So in traditional ecosystems, if you wanted to deploy a new application, you might want to go through and actually look at the bytecode to see if anything in there looks suspicious. There's a well-known set of libraries that are open source on the internet that you can go and you can actually assert your binaries against, whether it's Java bytecode or it's good old-fashioned machine bytecode, and you can actually see if there's anything buried inside of that that you potentially would not want there. We have the same concept with images in a cloud-native ecosystem. The same paradigm applied in a different, more distributed way. Code reviews, right? So you and your team going and looking at what the actual code does. Is there any vulnerabilities? Are you catching your errors? Do you have exposed sockets? What happens if somebody floods the socket? Just being security-minded throughout your day-to-day life is another big thing that I've been obsessing over. So these are all tools that you and your team could use to prevent unwanted behavior. But as we all know, bad things can still happen. CVEs still happen, right? There's no such thing as perfectly safe and perfectly secure and perfectly perfect software, right? FreeBSD, Linux, Kubernetes, name an open source project, Jupyter Notebooks, they've all had CVEs opened up against them. They've all been exploited at one point, and they've all been fixed. But somebody had to discover this first. So this concept of detection is the scientific approach to looking at our systems from the bottom up instead of from the top down. So by taking things that we would otherwise be effectively blind to and asserting rules against them and using those signals for data processing, we're actually able to see things in our system that we otherwise would not be able to see. And so detection is this approach to looking at our system and saying 99% of the time it behaves in this way given these input signals. But on Tuesday, last week, all of a sudden this happened, and we have never seen this before, and we weren't expecting this to happen, and we can programmatically assert that there was, we would call this an anomaly, that there was an anomaly that happened in our system. And that is where detection comes into play. So some people use tools like observability to do this, right? So whether we're auditing cloud infrastructure or the application itself, or the Linux kernel that you're running on, or the Kubernetes audit logs, we basically just want to have visibility into our system with high cardinality across the whole stack. We also look at things like intrusion detection, right? There's been a couple of exploits over the past year where folks have found out that people scan images. So people scan PDFs. And if you upload an image with thousands of URLs buried inside of it, or a PDF with thousands of images buried inside of it, you can effectively DOS someone unintentionally or intentionally. So there are ways of getting things into a secure system, and you may not be aware of a certain vector. So security is this whole concept of studying these attack patterns and the humanistic approach to how somebody might think of being intrusive in your systems. And so I've done that with Kubernetes. And I think the approach to preventing this from happening, to securing this, and detecting something that is malicious that could be going on, is this word that I have been using that I would like to start advertising, pull requests accepted if you don't like it, called runtime security. That is a hybrid of both. The practice of using something like Kubernetes access control or policy enforcement to prevent unwanted behavior, but also understanding that in some cases that might not be enough. So we can begin to use tools like observability tooling, like Falco, what you're going to see in a moment, to actually audit the kernel and understand what's happening in our system. And I believe that having both of these creates a set of checks and balances where an operator or an infrastructure engineer could go in and not only prevent unwanted behavior, but detect it, and then after they've detected it, go through and create new policy to prevent it from happening again. And I think this is a complementary approach to understanding our systems and to securing our systems moving forward. Okay, so I'll give you the 30-second pitch on Falco. Don't worry, we're going to compile it and actually run it so you'll be able to see concretely what it does. It's a CNCF incubation project. Who here has ran Wireshark before? Okay, I really wish we could have seen that, but everybody in this giant auditorium just put their hand up. So Laura Stujani, my boss, the founder of the company I work for, Sysdig, was one of the original creators of Wireshark. He has his PhD in Linux. And his original thesis to solving this problem of understanding our systems was that TCP is the fundamental packet of truth, right? It's the atom, it's the quark, if you're into quantum mechanics, of how we understand computer science. As we moved into cloud native, as we moved into computers, we realized that the network isn't necessarily the ultimate source of truth anymore. So what we did is we started to look at kernel tracing. Who here is familiar with kernel tracing? Okay, so maybe a third of the room just put their hand up. Leo put his hand up. And there are a couple avenues for how you would potentially trace events in the kernel, but the idea here is that if all software ultimately flows through the system calls in the Linux API interface, by auditing these system calls at runtime, we should be able to understand exactly what's going on in our system and gain otherwise unavailable information about what potentially is happening. So this is where this whole observability thing comes into play. So Falco has taken this enormous onslaught of data from the kernel globally. So if you use something like ptrace, I mean, by definition, P stands for process, it's concretely married to a process itself with a PID. What Falco and what the Sysdig CLI tool does is it has some libraries that allow you to go through and globally audit what's happening in your kernel. The two ways we do this is by either running a kernel module or by using a newer technology called eBPF that allows us to implement kernel tracing in user space so that we can understand what's going on in the kernel. What Falco does is it takes this stream of data, these signals from Linux, and it asserts them against well-known anomalies, right? What happens if somebody executes open, the open system call, against Etsy Shadow? Do you and your team want to know about that? I probably would. And if you're savvy, I got to use the word savvy in my presentation, if you're a savvy Linux user, you could probably find ways of doing this on a system with the system and user space not being aware that you did this. But the kernel ultimately would have to execute the system call. So by going to the kernel level, you're able to see things you would otherwise be blind to. So again, it's an evolution of Wireshark, but for the kernel, and this allows us to begin kernel tracing. So how does it work? So Falco takes not only information from the kernel, but also other bits of information from a containerized system as well. And we're just using what's going on in the kernel to tell a broader story about how we would potentially be detecting anomalies in Kubernetes. I like how people are taking photos of my very professional ASCII diagram on the screen here. I mean, come on, I went through and actually centered this with spaces and counted the spaces. This took like at least 20 or 30 minutes. So on the left side here, we have system call events, is what I basically just described. We also can parse other bits of meta information from our systems as well. Who here has ever explored the Docker socket? Handful, another third or so of the people here. If you can actually go and connect to the socket, you can actually get all kinds of interesting meta information about the containers that are running on the system. Kubernetes also gives us some visibility as well. We have Kubernetes meta information. What is the name of the pod? When was it started? How long has it been running? What namespace is the pod running in? And we also have this new feature in Kubernetes called Kubernetes audit logs that basically give you the who, what, why, and where of something happening, of some mutation in your infrastructure in your system. So if you ever go and follow the tutorial online and blindly download a YAML manifest and apply it to a cluster and just kind of hope it works, which we've all done before, I'm sure, what's actually happening is you're mutating the data store in Kubernetes, and then all these little controllers come out and they go and they try to reconcile this new configuration that you've pushed to your cluster, and if you're lucky, it should work. So by having this central database, we're able to tell an even broader story about what's happening in our system. So all of this data comes into Falco, which is written in C++, and it's highly optimized for efficiency here. I mean, we're dealing on the order of magnitude of millions of system calls potentially a second coming up from the kernel. And how it comes up from the kernel is over a ring buffer. And Lorenzo Fontana, probably the most technical maintainer on the Falco project, sitting in the front row here, that's an inside joke of ours. He gave a wonderful talk earlier today about eBPF. He literally wrote the book on BPF. There's in that the slide I asked you to take a picture of, you can go watch his talk. And he goes into much more detail here. But basically, we have a 16 megabyte ring buffer per CPU running on our system. I'll show you concretely in a moment what that looks like. And we're able to pull these system calls up through that, combine that with Kubernetes information, combine that with the container information, and then assert this against well-known security anomalies. Once an anomaly is detected, there's a few things Falco lets us do. Fundamentally, Falco is designed to be composable, so you can take an output from it and you can plug it into anything you want. The first one we see on the screen is gRPC. This is relevant because this has allowed us, using tools like Protobuf, to easily build clients and SDKs for you to plug Falco outputs into other arbitrary parts of your system. Right now we have Rust, Go, Python, and if you would like to generate your own, pull requests are accepted. We also have a concept of a webhook, of actually going out and trying to send data to a configured web server. And in this example that I'm going to be running today, good old standard out, which we're just going to look at in the terminal here. So again, to summarize, from the bottom up, we have the Linux kernel. On top of the kernel, we have either a kernel module, which we'll go more into what that looks like in a moment, or an eBPF probe. Then we go into our ring buffer that basically runs on that thin layer between the kernel and the rest of user space. And we move up into user space where we have two libraries that are able to pull information from the ring buffer. And then ultimately, Falco is built on top of all of these libraries and allow us to interface with Kubernetes and Docker and actually tell a full, holistic security story. So to summarize, Falco is a static binary. You can run it potentially in a container. It's written in both C and C++. We have Rust, Go, and Python clients, and this whole thing has been optimized for speed. GitHub.com/Falco Security if you want to see more. So let's talk about the kernel module. So what this does is this parses system events. So kernel modules were our first approach at how we would go about configuring custom logic in the kernel. There's a fundamental problem with this, which is if you're running a potentially unknown kernel configuration, or if something happens on your hardware or something that you didn't plan for happens in your kernel module, you can potentially crash a system. Furthermore, imagine me, a security engineer, like walking into a company and saying, "Hi, download our kernel module from the internet and install it in production. We promise that's going to be a good idea." So this problem is why eBPF is so successful. eBPF says, we're going to take the BPF, Berkeley Packet Filter, and we're going to go a step further, and we're going to start to build more logic and more capabilities into this very old, otherwise relatively unused part of the Linux kernel. And what we're going to do is we're going to guarantee a few things, and particularly we're going to solve this kernel module problem of if you want to do certain things, we're going to prevent you from being able to crash a system. So we started to play with eBPF. So we wanted this to do the same thing that our kernel module was doing. We wanted to parse these system calls because we have found that this is actually a good source of truth for doing things like detecting anomalies. And we also wanted to make sure that we couldn't potentially crash a system. So because eBPF code is already pre-compiled into the kernel, you're effectively just telling the kernel to turn it on, right? It's just like JavaScript running in your browser. It's just saying, you already have this logic, just please do this one thing for me, instead of please run this logic I wrote myself. So BPF, or eBPF rather, it's unable to crash the kernel, it's effectively read-only, and it's not Turing complete. But you're still able to do some pretty powerful things with it, and then once you get it from the kernel, you can implement that in a Turing complete language of your choice. So if you want to look more, go to the open source project and check out scap.c and scapbpf.c. Who here remembers Wireshark cap files? Same concept, but with BPF and for the Linux kernel. So earlier today, I met with a guy, Gares, if he's here, thank you for helping me out earlier. And he helped me get OPA, or Open Policy Agent, set up for my demo. And we're going to actually hack into Kubernetes, and then we're going to go through and use this to prevent my hack from happening again, and we're going to run a series of experiments here. More on OPA in a moment, but basically it's a CNCF project just like Falco, and it works with more than just Kubernetes. So it doesn't have to work for Kubernetes, although in this example we're using it, and it was designed to basically just solve the problem of creating a policy engine that we could implement anywhere. So one policy engine to rule them all is basically what I think of when I think of OPA. Gatekeeper, an open source tool, is an implementation of this broader policy enforcement mechanism, and Gatekeeper is specifically coupled with Kubernetes, and that's what we have running in my cluster. So if you want to run something like OPA or OPA in Kubernetes, Gatekeeper has sort of taken this existing, more flexible, more modular project and optimized it for a single concrete use case of Kubernetes. Okay, so let's talk about my demo. Looks like we are 25 minutes into my talk, so I'll probably do another 10 or 15 minutes here of this demo, and I'm going to go pretty fast. So I'm going to leave some questions at the end, so if something doesn't make sense or if I skip over something, please either ask me afterwards so I can document it on the internet. I'm sure you're not the only one who had this question, or even put your hand up at the end, and I'm happy to answer quickly at the end of the demo. But what we're going to do is we're going to start off by showing you how we're doing some kernel tracing on my local laptop here. So I'm running Arch Linux. I have a fairly old kernel, not too old, but also not like brand new, to kind of demonstrate what I would think most people are running in production. And we're going to create a user local bin FOSDEM on a couple of different environments. The first one on my local laptop, and we're going to parse this using the kernel module. And you're going to see the devices, and you're going to actually watch me load the kernel module on my laptop. The next one, we're going to start Falco with BPF, and I'm going to delete the kernel module, and you'll see the devices go away, and you'll see Falco still working dynamically, which is exciting because we didn't have to load anything into the kernel. Next, we're going to do this in Kubernetes again, and we're going to do this by, we're going to have a cluster administrator kubeconfig configured, which is basically like root on my Kubernetes cluster. And then I'm going to use Kubernetes access control and prevention techniques, RBAC, to create a new configuration that only gives me access to one namespace in Kubernetes. I'm then going to create a shell in Kubernetes, privilege escalate through that shell, gain access to the underlying node, get root access, all of which that should have been reasonably prevented given Kubernetes RBAC. After we do this, and I've hopefully sufficiently scared a number of people in the room here, we're going to go through and we're going to look at the OPA policy and the gatekeeper policy of preventing this from happening again. And we're going to look at how Falco, the whole time, had every system call and was able to tell a story about what happened and basically explain the threat model and the attack vector for what was happening in Kubernetes. Okay, so done with my slides. So the first thing I'm going to do is I am going to show you my /dev on my file system here. Can everybody see okay? Cool. Change directory /dev. You can see here we're looking for Falco down here in these devices. And if you notice, you don't see them. So next I'm going to go to this directory in home here, and you're going to see I have two precompiled objects here, one of which is a kernel object that we're going to load as a kernel module, and the other one is just a regular old elf object, and we're going to use both of these subjectively as we start running Falco. And so what I want to do is I'm going to just run sudo falco, and let's see what happens. Let me enter my password here, and you can see here we got an error, unable to open device falco.0. Remember earlier I mentioned a 16 megabyte buffer per core. I have 8 cores on this machine, so we're looking for 0 through 7, right, 0 index, device files that do not exist. So what we're going to do is we're going to insmod falco probe.ko. And if I list mod and we'll grep for Falco, you can see it's loaded. And if I list /dev again, you can see here we now have Linux devices for every one of my CPU cores. So now we have something that's coming from the kernel. And this ring buffer is iterating around and around over itself in 16 megabyte increments, and nothing is pulling from it. So we start from Falco, and now we're actually able to gain data. So Falco is doing nothing, right? Nothing's happening on my system. I'm running a pretty primitive system here. I have an IDE and a couple of folders open from when I plugged my phone into my laptop. But even if I had Chrome running right now, you would see some set GIDs and set UIDs, and you would see Falco starting to alert us that something was happening. So for our first experiment, in a different terminal, sudo, or actually we'll do this without sudo first, user local bin FOSDEM. Permission denied. Linux is using preventative action to keep us from doing something that we shouldn't be doing. We escalate to a user. We happen to know the password. We're able to create the file. Falco alerts us. Pretty simple alerting mechanism here. And you can see here that because this was a well-known directory, I'm sure most people in the room here is familiar with user local bin or user bin, as well as maybe some other files on the system, such as /proc or /dev. There's a lot of things that you would potentially want to know about if somebody's executing open system calls on some of these directories or on some of these files. Perhaps PID1 would be of interest for some folks. So we're able to take this a step further, right? So we're going to keep Falco running, and I'm going to get some space in here so you can see the alert as it comes. And this time I'm going to run a Docker container locally, and we're going to perform the same experiment. And I want you to see how the Linux kernel treats a containerized instance versus a local instance, because this is the fundamental technology that empowers all of the security parsing that we're doing. So I'm going to Docker run IT. I have what I call it my hack container. But basically, this is a container that just has like netcat and nmap and some bash aliases and a lot of goodies that I use to explore Kubernetes. And I just push this whenever I make a change to it. So I'm going to run this locally. You can see here I've got 2 commands that might be interesting to you that we're going to use in a moment when we run in Kubernetes. And you can see I'm root here on my my system. If we uname -a, you can see I'm running Manjaro Linux kernel version 4.19. And this is the kernel on my system, right? This isn't some newly invented magical virtual kernel or anything. This is just the application running in the context of C groups and namespaces interfacing with my existing kernel. So touch user local bin FOSDEM. You can see here, except for this time, if you look at the end, you can see we're able to get information from the Docker context. We're able to get the name of the image that executed this command as well as the image ID. So Falco starts to pull information from our system as things happen at different layers. And if it's running locally, we're able to audit it, but if it's running in a container, we're able to get even more information from the data streams that exist in a containerized environment. Okay, so let's do this in Kubernetes. So I'm going to go back to my public speaking repo here. Slides, clusterfuck. Cool. And I'm going to alias k is equal to kubectl. And I'm going to k get pods. So, oh gosh, FOSDEM Wi-Fi, come on. There we go, no resources found. I'll try to keep the internet to a minimum here as we wrap up my talk. But you can see there's nothing running in the default namespaces. And I'm going to use namespaces as a way to demonstrate that I do in fact have global privileges on this Kubernetes cluster on this system. So I'm going to list namespaces. So I get namespaces, and you can see here I have Falco in the Falco namespace, Gatekeeper and Gatekeeper system all installed. So if I go to my config directory, .cube.config, .cube, and list in here, you can see I have config, config admin, and config default. Admin is the one I'm using now, but if we copy config default over here, it's still going to be interacting with the same Kubernetes cluster, except this time we're going to be using a different service account, which means this user that I'm now running as should not have access to these namespaces. And the simple trick here is we should not be able to list namespaces. So kget namespaces, and you're going to notice and see that the Kubernetes API server rejected this request. It's preventing us from doing something it doesn't want us to do. But as a savvy computer user, we understand that there may or may not be ways around this. So let's go now, still as my default user, without access to the rest of the namespaces in my cluster, we can list pods, and we can list pods in the default namespace, fine, but if we try to list pods in a different namespace, we happen to know Falco exists, you'll see again that it's going to get rejected. So here in my clusterfuck FOSDEM 2020 directory, I have a small bash function called shell. And you go in here and you can see that we have some very interesting configuration bits defined, as well as that original Kubernetes cluster container image that I ran moments ago on my local laptop, and we're going to run this in Kubernetes. There's a few bits of configuration here that we're going to prevent from happening again using a tool like OPA, which is this very lovely security context privilege equals true. So Kubernetes is an abstraction, right? And because of this abstraction, you may not quite understand truly what's going on as you go down to the internal layers of the system that's running Kubernetes. And basically what's happening here is that we're able to go through and escalate privileges and exploit this cluster. So I have 5 minutes left, and then we have 10 minutes for questions. So I'm going to go pretty quick here. So what we're going to do is we're going to run this function shell. First, we're going to source it. Now we're going to run shell. And so what this is doing is it's basically creating a TTY in my container image running in Kubernetes. And here I am. I'm root at shell. As the user in the container, I can do a list, and you can see that I'm in the root file system of my Linux system. But if I cat out etc motd, you're going to see there's two commands here that we're going to use. Because privilege is equal to true, I'm able to go through, and I'm able to jump into the PID1 namespace, as well as the mount, the user, and the network namespaces, and I'm able to basically build a TTY through this such as this. So now, I'm actually going to do this with bash at the end, sorry. Bin bash. Now you can see I'm IP at 172.20.35.32, which if you've ever run an EC2 instance before, you'll know that this looks like a default VPC Amazon instance ID. And if I list where I am, you can see now I am actually on a different file system than I was before, because I escalated to the mount namespace that the container had access to using an senter. To give you an example of where I am and what's going on, I'm going to do a Docker list, sorry, Docker PS, and you can see all the containers running in Kubernetes as the user of the Linux system that Kubernetes is running on top of. In Amazon Linux, there is a well-known IP address that looks like this. Thanks. I'm just going to do this so I can copy it. Sorry, I'm trying to go fast here. Oh, thanks. I know. Cat, etc, motd. Sorry, FOSDEM Wi-Fi is hard. We're going to run our, enter again, run our curl, and then we're going to actually build this request. We're going to go to the 2019 API 10.01. You see here we have user space. This is where things are about to get exciting. And did I spell this wrong? I hear a lot of mumbling, but I can't understand. Data. User data. Thank you. All right, there we go. So if we scroll up, this is the configuration file that cops use to bootstrap Kubernetes. And as I get this from the Amazon meta information, I come in here and I can actually see that this was hard-coded on the system. And we have not only privilege equals true, so we're going to do a grep for -i priv, but we can actually get -i config. And you can see that I was able to get the kubeconfig path on the system and cat this out. Here, poof, root cluster access from kops running in Kubernetes, what I would otherwise not have access to. There's my cert material there on the screen. I would be able to copy this down locally and basically escalate my way to the rest of the cluster and exploit Kubernetes while it's running unsecure. So if you're not already preventing this from happening, I'm going to show you how to do it. So what we want to do is we're going to go back to this directory here, and I have some OPA policy that's going to get installed with Gatekeeper that if you want to go and actually look at what it's doing, it's a lovely set of default policy. And we're just going to kapply -f gatekeeper.yaml. And what this is going to do, remember, I'm still this default user, but I was able to escalate my way through to get the root config. What OPA is going to do now for us is it's going to prevent this from happening again. Why did this not work? Oh, yeah, thank you. It doesn't work because RBAC is preventing us from taking action in this. Default, nope, admin to kube config, yes, run this again. And so now OPA is going to prevent us from taking action again. And if I try to run my shell again, you're going to see here, it's effectively denying this request. So what does Falco have to say about all of this? So I have an alias here called Falco logs. And if I can run that, and basically all it does is it's going to run klogs minus label app is equal to Falco in the Falco namespace -f. And this is where the whole lesson comes to life, right? This is where we can actually see from the Linux kernel what was happening on those systems that are echoing these alerts out to standard out, and we're actually able to create this policy to prevent it from happening again. So the story here, if we look at our alerts that we're getting, it's pretty concerning. First, my container happened to swipe our bash history away, and we're starting to get information from Kubernetes and from Docker. We're going through and we're creating new shells. We started a privileged containers. Falco was able to alert that to us as well. And here at the very end, you can see the big exploit itself, privileged containers stacked, and that's where I started to escalate into different parts of the system. So the story here, the threat model here is there are ways of hacking around things if you're not taking preventative action. But in some cases, that might not be enough. And so being able to detect these types of events and these types of anomalies using tools like eBPF allow you to do it in a safe way so that you and your team and your infrastructure can begin to have this sort of checks and balances as you go back and forth between security approaches with prevention and security approaches with detection. So if you want to get involved with any of these projects, they're all CNCF projects. Myself and I'm sure many other maintainers here would love to have you involved. So feel free to reach out to any of us. And if anybody has any questions, I think I have about 7 or 8 minutes left. And while we have the environment on the screen, I'm happy to answer questions or show folks things or anything for that matter. So thank you all for coming. I'm Chris Nova. And then one thing, as people start leaving the room, if somebody has a question, I'm going to save the question back for the recording, so just try to be patient with us as we do the audio relaying here.
Can you take one or two?
Yeah, go for it.
Yeah.
Hi. And what is the performance?
I can hear you. Yeah.
What is the performance impact of Falco on?
One more. You have to yell at me.
Okay. What is the performance impact of Falco on systems?
Negligible. So the question was, and I'll say this for the recording. The question was, what's the impact of Falco on the underlying system? And my response was negligible. And the reason for that was because, again, 16 megabytes per core, and it's written in C++. So we've got some documents out there on the internet. I'll add one to the markdown document here, where we have folks running, upwards of 2,000 nodes in Kubernetes, all running Falco and still able to maintain their other production loads. It's fine. In fact, Skyscanner, a company just released a blog that I'll put a link to. They have wonderful metrics where they've been doing load testing and benchmarking with Falco, and you can see the performance of it.
I have another one.
Yeah, if you have questions, just come right up here, and we'll answer them for the recording.
How does this compare to the standard Linux audit framework?
How does this compare to the standard Linux audit framework? So it does similar things, but it takes it a step further when you start looking at how we're able to enrich that otherwise only available Linux information with Kubernetes, with containers, with other bits of information and data streams coming out of your system. We're right now building a new API for inputs, allowing dynamic inputs being loaded into Falco. So we could potentially start to stream information about I/O block devices, XDP, the rest of the Linux kernel, and other things happening on your system, and building hybrid objects with all of these input streams. That takes it a step further than Linux audit. The question was, do we plan to replace the Linux audit framework with Falco? Absolutely not. What we want to do is we want to make Falco and the community around Falco mature enough to where we can start to use tools like the Linux audit framework in conjunction with these other tools and assert rules against all of this information coming into Falco. Yeah, what's up?
Thank you very much. A really nice talk. My question would be, is it possible to turn the shield into a weapon, meaning that somebody using Falco and observing those kernel events and calls discover other vulnerabilities in the system by just playing around?
So the question here was, would it be possible to discover other vulnerabilities in a system just by playing around with Falco or just seeing what Falco has to say? And I think that was one of the lessons that I was trying to allude to, which is giving an environment where we're taking alerts like this. Potentially, this would be able to be your first glimpse into building the more mature threat model of understanding what actually happened. In my example, I just kind of did it in the reverse way, like I sort of did it backwards, where I showed you the threat model, and then I showed you what Falco has to say about it. But the idea here is that by detecting anomalies that you are well known in Linux, you would potentially be able to start a journey into discovering a CVE, remote command injection, a rootkit, whatever. Yeah. Yeah, does anybody want Falco stickers? There's got some more up here. Come here. Here. Sorry. I don't know how many are left. There's one. There's some there. Have fun. Any other questions? I'm going to kind of go stand over here if folks want to come meet me, but it's FOSDEM, so I got to get out of here and let the next person get ready. Thanks for coming, everyone.
Well, super cool.